what we're going to do is have a look at this. Right, this question is about insoluble salt, and they've actually told you that you're going to use the precipitation method. And what you do is you look on the reactants, not product side, sorry, and you end up with a precipitator solid. So these are all clues. And if you're fortunate enough to have a question like this where they lay it out for you, you've got to pick out the information. Right, but before we go any further, I just want to do this for those of you doing like triple science, not double. First of all, ask yourself, is it soluble? If it isn't and it's insoluble, you use something called the precipitation method. So you mix two solutions, one containing the correct positive ion, the other one the correct negative ion, right? And you're going to end up with a solid, a precipitate. Right, it's a bit long-winded this, but I don't want to rush it. Is the salt soluble? If it is, then you need to ask yourself, is it a sodium, potassium, ammonium? Is it sodium, potassium, or ammonium ion? Right, ammonium salt, sorry. If it is, then we go straight to the titration. And we normally react it with, I've seen more sodium hydroxide reactions than the others, right? But you can also get potassium and ammonia solution, but that's more to concentrate on that. But for now, if it isn't one of those three and it is a soluble, what you do is then you react the acid with an excess. So this is the idea. There's your acid, and you keep pouring in the metal or metal oxide, metal hydroxide, or metal carbonate. So the metal ion goes in here. Right, the metal ion goes into here. And then what happens is you pour it in, because it's reacting with the acid, that'll disappear. And then you pour some more in, and that'll disappear. And then finally, you'll pour it in, you'll pour it in, you'll pour it in. And as you're stirring away, that'll disappear, and that'll stop disappearing here. Once it stops disappearing, you know this has reacted. All the acid has reacted, and then you've got a soluble salt in there, and then you filter it to remove the excess solid. Then you put it in an evaporating basin, Bunsen burner, glass rod, pull it away, cool it. If you get some crystals, it's reached this point of crystallization, then you turn off the Bunsen burner, you cool it. Once you've cooled it, you then end up with salt. What you can do is then put it in a warm place to dry, or you can tap it with a paper towel. Right, this is what I wanted to show you. This is the key. You need to know this. So let's just get rid of all this. We can carry on with this. Right, let's continue with this. Right, describe how she could use the solutions, right, of lead, nitrate, sodium, bromide to obtain a pure dry sample of lead 2 bromide. Okay, 5 marker. Okay, so first of all, right, they've given you the two solutions, so you mix the solutions of lead, nitrate, and sodium bromide using a beaker and stir with a glass rod. That's giving some experimental details. Always good to do that. Right, once you've done that, what you've got is you end up with a the precipitate, which is the salt lead bromide salt precipitate is filtered off, or the residue, yeah, using, add another bit of, this is easy to put in because it's just using filter paper and filter funnel. Then what you do is you wash off with distilled water, and then you can leave in a warm place to dry. So these are easy marks. So if you look at the mark scheme, what you'll see is, look, that and that is a mark in itself for using experimental details, right? And then what they're saying, so you're saying mix the two solutions together, mix this and stir, yeah, stir with a rod, use filter paper and wash off with distilled water because there's no ions there to contaminate it, and then you leave in a warm place to dry. All these are the key words. It's a standard answer. Okay, it's a standard answer. Right, pure dry crystals of magnesium nitrate can be obtained from magnesium nitrate solution by crystallization. Okay, so we've got to put these in order. So allow the solution. So look, we've been given the solution. They've given us E, so that's gone. So now we've got to put in allow the solution to cool, evaporate, put crystal. Right, I know that goes at the end actually. Right, so that's that done. Put crystals. That's that done. Pour the mixture through filter paper, heat the solution, allow the solution to cool. Right. Heat the solution. Right. So B. Then you dip the glass rod to see if crystals form. Right. Once you've done that, you allow it to cool to room temperature. And then that finally leaves C. Right, these are good ones to get your head around. But be careful, don't commit yourself. If you need to put the sample here, or do it in pencil first, and then once you're happy with it, transfer it to there. Otherwise it can be messy. Then students start doing this sort of stuff, and then they're trying to put in there, and if you do that and you can't read it, you might lose a mark for no reason. Right, okay. Student obtains dilute sulfuric acid. Sorry. Student adds dilute sulfuric acid containing calcium chloride. He obtains a mixture containing a precipitate. So you've got a precipitate reaction of calcium sulfate in a solution of hydrochloric acid. Right, so they've given you a clue. Right, we know sulfuric acid is aqueous. Calcium chloride solution, they've given you a clue here. That's aqueous. And then you've got calcium sulfate. They gave you a, yeah, that's a solid. And hydrochloric acid is what? Aqueous. So they gave you those. Right, we need to draw a diagram. So this is quite straightforward. You draw that. You put the filter paper in here. And then the conical flask, you just draw there. Okay. Right. Right, so we're carrying on with this. You end up with a brick red color. Right, bear with me. Right, okay, let's carry on with this. So this is how I remember it. I think with all the climate change stuff going on, right, and you can imagine, you know, well, a couple of years back, she was a teenager. Right, okay. So she doesn't want people to increase global warming, CO2 levels. So she says to you, you can either ride your limousine, limo, sorry, or, now I'm exaggerating that, or, and then you jump over to copper, which is save the earth. So this is how I remember it, yeah? And have you noticed there's this L shape? And then you jump over to copper. Right. If you look down, let me get this. If you look down here, you've got lithium, sodium, potassium, and then you go across to calcium. So can you see this L shape? There you go. Right, and then you jump over to copper, which is here, the policeman. Right, so what did Greta Thunberg say? Ride, red, your, yellow, limo, lilac, or, we exaggerate the or, so it's going to be orange, red color. And save the earth, if you look at it from space, it's going to be blue, green in color. So this is how I remember it. So what you do is you look at your periodic table, you know this, right, just from studying the periodic table. So it's this L shape with a copper here. Copper, I think of a policeman in charge of making sure we don't pollute the atmosphere too much. So that's what I've learned it as, and yeah, it seems to work anyway. Right, okay, let's go back. So here, identify the ion because it's brick red. So brick red or orange red, it's going to be this one, which is the calcium ion, or Ca2 plus, because it's in group 2. So just why this ion is present in, right, okay. If you know the solubility, let's get rid of that, let's get rid of that, don't need that, that, leave that. Because the calcium is calcium sulfate is slightly soluble. Okay. That's silver nitrate. Okay, so I'm gonna we just do those. Right, you add silver nitrate, fluorine, chlorine, bromine, iodine, and astatine. We're not interested in those. Fluorine is too reactive in the lab, so we never use it. So I think of a white ice cream with a hint of lemon. Yeah, so I've got this ice cream, on a cone with a lemon in there. However, it does it right. Let's keep going. What would you observe in this test for chloride? You'd end up with a white precipitate. Name the substance responsible for this. It'll be silver chloride. Okay. He reads a textbook that dilute nitric acid should be added. Why is it what he does not need to add dilute nitric acid in this test? Does it give any details? Okay, yeah, because here you've already got hydrochloric acid in. Already have hydrochloric acid in the solution. Right, calcium sulfate. Right. Okay, so only 2 mark. I think they just wanted to make the marks up. So what you do is is impure, right? Because it contains some hydrochloride. So you can wash. What do you always wash with? Distilled water. And then you leave to dry in a warm place. Right, okay, there you go. Right, let's keep going. Dilute sulfuric acid can be used. This titration, okay, leave this. We can do titration on a separate titration. More calculations. No. Okay, let's have a look at this. Okay. Right, look, there's something simple like the diagram that you need to remove excess copper oxide. So remember, if you've got a soluble salt, it can be either sodium, potassium, or ammonium. Right, so sodium ion, potassium ion, ammonium ion, or it can be others. If you have these three, which method do you use to prepare these? It's called titration. Right, here what you've got is we add in excess metal hydroxide, metal oxide, metal carbonate it was. Right, but they've already given you that. They've got you to the excess part. So how do we remove the excess part? Simple. You get a filter funnel, filter paper, and that's it. And then you can just put it as a beaker. There you go. Right, we're not interested in that. Pure dry sample of cobalt 2 chloride. Okay. Let's have a look. Right, okay. So let's just read through that. So this is a soluble salt. How can you tell? Right, if you look here, where are we? Filter the final mixture to collect the filtrate. Right. When you filter something, you're removing excess cobalt 2 oxide. Right, so this is what's happening. I'll just try to explain this. It's a standard sort of way of doing it. So you've put dilute hydrochloric acid in here, right? Then what you do is you add cobalt 2 oxide here. So I've added it here. You get a glass rod and you stir it. And what will happen, let me get that, that will disappear because it's reacting with the hydrochloric acid. Then you add a bit more and that will disappear again. Oh, let's just delete that, that'll disappear again. And then you add a bit more and a bit more. Just say, right, what will happen is you'll stir it and this bit will disappear. So you're this here now, what color should we use? Okay, can you see this bit of cobalt 2 oxide that's left is the excess. Then you filter it, so you'll get a filter funnel. I'm going through all the details so then it sticks into your head. You get filter paper, you pour this solution into here, then what happens is the excess cobalt 2 oxide goes there and you've got the filtrate in here. Filtrate. You end up with copper, well, look at this, cobalt 2 chloride solution. Yep. Then you put it into a evaporating basin, you heat it, you dip in a glass rod, cool it down. If it crystallizes, you turn off the gas or the Bunsen burner, you let it cool. It's exactly what we went through earlier. You let it cool, crystals form, and then you leave it in a warm place to dry, or you tap it, pat it dry with a towel paper. That's what it is. Okay. Right, okay. So now you're feeding. So let's get this right. Let me try this again. A sample of cobalt contains a small amount of solid impurity that dissolves in water but does not react with the acid. State why it is not necessary to have a precise measurement of the volume of hydrochloric acid in step 1. Because you're going to have the cobalt 2 oxide is going to be in excess. You're going to keep pouring it in, so it's roughly 50 centimeters cubed. Yeah. Or you can answer it from the other side according to the mark scheme where they're saying, what do you call it? Because all the hydrochloric acid will react. State why the acid is warmed up. It's to increase the rate of reaction. Suggest why glass rod rather than metal spatula. So okay, because the glass does not react with the acid, whilst this metal spoon will. State how the student will know when the cobalt oxide stops reacting. Well, okay, it will stop disappearing. It will stop disappearing. sometimes they can ask you that question from the other side. How do you know all the hydrochloric acid has reacted? Because it will stop, the cobalt 2 oxide will stop disappearing. State why the method used in step 6 will not produce. Where's step 6? Leave the filter until all the water has disappeared. Okay, yeah, because look, here the sample of cobalt 2 oxide contains a small amount of solid impurity that dissolves in the water but does not react with the acid. So the soluble impurity also be present in the crystals. Right, okay, 5 marker. Describe how the student could produce pure dry samples from the filtrate. Okay, so they've taken you to this point. You filtered it, you removed the excess metal. What was it? Cobalt 2 oxide. Right, and now from this solution here called the filtrate, what do we do? Right, it's gonna be, we're gonna say add to evaporating basin and heat using, they like to see details of experimental equipment, and heat using Bunsen burner. Then test with a glass rod to see if it has reached its crystallization point. Once it has, you turn off the Bunsen burner and leave to cool. Wash crystals with distilled water or deionized distilled. I use the word distilled water because it doesn't contain impurities. And then leave crystals in a warm place to dry. So can you see this constantly repeating the same thing? So if you know how to do it once, learn it and run with it. That is titration. We're not interested in titration. Not interested in titration. Right, that's what we're interested in, but we'll do that in the next video. Okay, assalamu alaikum.